Hello friends, I am Amir Nizami and today we are going to study the functionally graded material plates. So what are the difference between the laminated composite plates and the functionally graded plates, we will see, and why the functionally graded material plates are used, or it is also called advanced composite plates. So first of all, we will see that the composite plate structures are having a lot of applications. Basically, we can see here that in the windmills, these are used, and in the aerostructures, in aeroplane, we can see that the aeroplane is made up of composite plate structures. And then here we can see this electric pole that is also made of the composite plates. Then here we can see the boat, sailing boat, and the ships. They are also made up of composite plates. Okay, so these composite plates may be of the functionally graded material plates, or it may be the laminated composite plates. And which one we have to use and why we have to use, we will see. Further, we will see that the helicopter and then rocket and these satellite instruments and the drilling machines, these all are made up of the composite plates. So it is having a vast application. So above where the macroscopic, we can say, the applications, and we are also having the micro or nano uh, applications. So we can say that, okay, micro electromechanical sensors, these are also used in the microelectronics chips, mostly in the electronics domain. Okay. So basically what we say that the composite plates are made up of two or more different parts bonded together. So the definition of composite implies that it is a material or things are made up of two or more different parts. So in the laminated composite plates, what we say that each lamina is made up of uh, fibers and the matrix. And here we can see, or we can say that the functionally graded plates are made from the one end is of metallic and the another end is of ceramic. So basically, uh, we can say that two or more different parts bonded together. So that's the composite material. So high specific strength are the properties of the composite plates. It shows very high specific strength, high specific stiffness, lightweight, thermal resistant, and corrosion resistant. These all properties are very useful. Basically, we use in the aerostructures. If it is lightweight, we know that the fuel consumption would be less. Okay, thermal resistance means that at a high elevations, we know that the temperature difference are very high, so it would be very useful, and it is also corrosion resistant and high specific strength. We require very high strength as well as high stiffness. Now, further we see that, okay, classification of the composite plates are done on the basis of the plate size. So it may be the macroscopic or macro scale, and it may be the micro nano scale. Okay, so plates are, we have seen that in the macro scale, the application was in the domain of aerostructures, and in the micro nano scale, we have also seen that in the electronics domain, micro electromechanical sensors and all chips, it is used. Then these both are having one materials degradation. Further classification of both micro scale and macro scale is done with the materials degradation. These material degradation shows that it may be macroscopic grading or it may be microscopic grading. So what these sense? Let's see. Uh, if we say that, okay, this is one lamina and this is another lamina, lamina 2, and this is third lamina. So we are just seeing along the thickness of the plate H. You may say that it is the x-axis and it is here the z-axis, and y-axis you can see that plate length would be like this. So this plate is having layer 1, lamina 1, lamina 2, and lamina 3. Okay, and this is the total thickness H. So these gradation are at the macroscopic level. this lamina may have different material properties, this may have different, this may have different. Okay, so it is at the macroscopic level, the material properties are changing at the macroscopic. Okay, so we can say that gradation is done, gradation is done at macro, MACRO, macroscopic gradation, scopic level. Okay, while this is the example of laminated composite plates. Laminated composite plate. Okay, and the second one we can say microscopic grading. Microscopic grading. So when we make the functionally graded material plates, FGMP, it is the FGM, functionally graded material plates. This name itself says that it is functionally graded, means at this level, at the bottom, we say that it is having completely metallic properties, and at the top level, it is having completely ceramic properties, ceramic properties. Okay, so the material properties are changing at the micron level. Okay, this these are changing throughout the thickness. We can say it's X and it is along Z. So the material properties are changing along the thickness at the microscopic level, micron level. Okay, micron level. We can say micron level. The changes. So material properties are changing, and those change can be done by two laws. That's the rule of mixtures are there. So that may be the exponentially varying. Okay, so these are the various, we can say that the gradation. So microscopic gradation, we can say it is the functionally graded material that is varying from bottom, means metallic properties, then at the top it's showing the ceramic properties, and the variation is done at the micron level. So we will go back to it, and then we have seen that this gradation, grading is the laminated composite plates, while the microscopic grading is for the functionally graded plates. Then for both type of plates, laminate, either it is laminated composite or functionally graded, we have the structural analysis theory. Okay, and that may be divided in the equivalent single layer theory and the three-dimensional theory and the discrete layer theory. That may be, we can say that it may be layer wise theory or zigzag theory. Now we will see the size dependency of the composite plate. So micro nano plates also. So here that is the size dependency. What is there? One process is the simulations and another is the experiment. So uh, one simulation process is the study of molecular dynamics. Another is the non-classical continuum mechanics. So that is having three theories: non-local elasticity theory, strain gradient theory, and the refined micro couple stress theory, or the modified couple stress theory. So we don't have much interest in it right now. We are seeing for the macroscopic level. So just I've just given an idea for this. So why we use the functionally graded material? So the first question we in our mind comes that why we came to the functionally graded plates? Why not this uh, laminated composite plates? So we can see that laminated composite plates are having one drawback. That is a very major drawback. What is that? That it get delaminates, okay, from its interfaces or at its interfaces when the material properties are changing at the macroscopic level. So the gradation due to that it changes. So we can see that in this level, at the interface level, okay, the material properties, if the material properties are different and it is bound with some glue, okay, that is glued together, and if the shear strength somehow increases or uh, just exceed the level, what happens? It get delaminated. It get cracks or delaminated from its interface at its interface, and then the structures get failed. So we will see here the same, that it get at the interfaces, it get detached, and due to that the failure occurs, and we can see the real failure here, that how it failed here. We can see this is the aeroplane wings, and this get delaminated. We can see the delamination here, how it get delaminated, and further the structures gets failed. Okay, if the wings get failed, we know that the whole plane will get affected with it. So this is a figure for the functionally graded material plates. It is shown that the bottom is the metallic and the top is ceramic. Okay, the length is A and the width B, and how it is shown that, okay, this uh, is having the variation of the material properties throughout the thickness at any point of Z, that may be Em, that is the metallic properties of Young's modulus of the metal, minus Ec, Young's modulus of the ceramic part, into V by H. H is the total thickness of the plate, plus half to the power n. N is the variational coefficient, okay, or constant, plus Ec. Ec is the Young's modulus of that. So if we put, or if we have n equals to uh, 0, then what would be this value? This value would be 1. Then if you multiply, then Em minus Ec into 1, Em minus Ec plus Ec, then we will have, let me show here, Em plus Ec minus Em into, it is the value of E of G, into V by H plus half to the power n. So if n is equals to 0, then E of Z would be equals to Em plus this all would be 1. So Em plus Ec minus Em. Em would get cancelled. It would be only Ec. So E of Z would be equals to Ec. Means when n is 0, then it corresponds to fully ceramic properties. Okay. So we will see here that the functionally graded material properties achieved by continuous changing the volume fraction of the constituent materials, usually in the thickness directions, and then it eliminates interface problem. So there is no interface problem now, because it is continuously varying throughout the thickness of the plate. Okay. So we can see from this figure also that power law is used for this functionally graded plates, and this material properties or modulus of elasticity is varying. Okay, this is varying continuously throughout the thickness using the power law. Then it eliminates the interface problems. There are no interfaces now. Okay, it's continuously there. Then the compositionally graded, often ceramic at the top to metal as bottom. Metal is at the bottom and ceramic is at top of the plate. And what's the advantage of the ceramic? We know that ceramic offers the thermal barrier effects. It is very good in thermal resistance. Okay, so we know that very high temperatures, if any uh, uh, airway structures are subjected to very high temperatures at high elevations, what it can take very high thermal loads. Okay, it can carry the ceramic part, and the metallic part is having advantage of, we know that it can have, or it can provide the ductility to the materials. Okay, so ceramic is non-ductile, or we can say that uh, that is brittle, while the material metal is uh, very ductile. So the composition of both make the structures in between that. Okay, so therefore the metal is very highly deformed. We know that it get deformed, or it get buckled at very low temperature, but ceramic is having the advantage that it can take very high load and it would not buckle. Okay, so the composition of both becomes very nice function. Okay, therefore these ceramic and metals are used to make the functionally graded plates, and the gradation are done with one rule is the power law, and another is the exponential gradation in both ways, and one is also sigmoid law. So these are the general law used to vary the properties of the material throughout the thickness. So we know that analysis of the laminated composite or functionally graded material structures are done by the three ways. One is the anisotropic elasticity equations. So first of all, we will see that whether the material is orthotropic or isotropic. Generally, in the functionally graded material plates, in plane we have the isotropic properties. Okay, and then structural theories that may be equivalent single layer theories, 3D theories, or discrete layer theories, and then the analytical or computational methods, whether we want to solve it with the analytical method or Navier's solution, or otherwise we can use the computational methods, finite element method and all. So this is written for the orthotropic lamina. So generally we know that laminated composite plates are orthotropic, therefore it's shown. And the same concepts of the laminated composite plates what we have studied before. So that would be used at the plane stress condition here also in the functionally graded plates. And the same stress strain relation would be used just if the material properties is isotropic in functionally graded somewhere, then E1 E2 would be equal to E. And these are the analysis theory that it may be equivalent single layer, three-dimensional, or discrete layer, which we have studied in the laminated composite plates already. So this is the classical plate theory, then first order shear deformation theory, higher order shear deformation theory, refined plate theory, Quasi-three theory. Similarly, in the discrete layer theory, layer wise, that is the layer dependent, whereas in refined zigzag theory is layer independent, that is the C0 continuous. So the theory is written for the equivalent single layer theory, which we have studied, and these are the displacement fields for the classical plate theory. We will not go in detail because we have already studied these things in the laminated composite parts. So this is the first order shear deformation theory, and the displacement fields and the strains are written here. Similarly, this is the third order shear deformation theory. Okay, here we are having the Z cube. Okay, so cubic variation of the in-plane displacements. Then further it is the quasi three-dimensional shear deformation theory, which is very much famous in the functionally graded material plates. It is used because we can see that here W naught of xi plus G of z. So here W is a function of z also. So transverse displacement would vary. It would not be constant throughout the thickness, but it would depend upon the z. Okay, so it's a function of gz. And then refined zigzag 3 are also used, and we will see now the code for this. So first of all, before that, we will see the paper, one of the paper. So we will see this. This is a paper by Ashraf, Zenkour, who has worked a lot in the functionally graded plates. So from, I think it is of 2013. So a simple four unknown refined theory for bending analysis of the functionally graded plates. He has used a refined trigonometric higher order theory is used. also satisfies the free surface conditions, means top and bottom. This is traction free or shear free. And the number of unknown functions involved in the present theory is only 4. 4 unknown are there, less than the reduced theory, which is having the 5, or the first order shear deformation theory, which is also having 5 unknowns. It is having less than that, means 4 unknowns, and also it is having the transverse stretching part, means transverse displacement is varying throughout the thickness. So it's a very good theory and very much successful in the case of functionally graded plates. So here this displacement fields are written for that, linear and as well as FG, and we will see FG is written below, that what is the function here chosen. So somewhere it has h by pi sinusoidal pi z by h. Okay, and here so we can also see that EG, material properties variation, that EM plus EC minus EM into this. Okay, if we put this K, there we have seen N was 0, here it is written with the K, denoting with K. So if K is 0, it would be 1, so EC minus EM, so EM would get cancelled, so at K equals to 0, EG equals to EC, means only fully ceramic properties would be shown. So we will see where the FG function, yes. So here FG function is shown here, that is written FG is h sine hyperbolic g by h minus 4g cubed by 3h square cos of hyperbolic half, and g of g is 1 by 12 times f prime g. So here it's also shown the results for the in-plane displacements. Okay, so we are going to run the code for that. We will see. We will just have these functions fg, and the gg function is written here. So fg is 2h is the total thickness, means that is nothing but a small h into sine hyperbolic g by h minus 4 times g cube upon 3h square into cos hyperbolic half. The same functions which we have seen right now in the this is the same equations I have written here. Okay, so we will see, we will run the code and we will see how it's distributed for the various layers. So material properties are also given. For the ceramic, it is 380 GPa, and for the metals, it is 70. And Poisson's ratio, we can see that for the metal and the ceramic are constant, that is 0.3. And we can see that Q1, Q2, Q3 are calculated in the similar fashion. So we will see that what we get the results. So first of all, number of composites. So that is functionally graded plates, but if it is sandwich one, and then that would be the case. So let's see, number would be 1 only, single. Height of the laminate we are taking 0.25, and along the x direction means length A, that is we are choosing 1, along y also 1, and thickness that is 0.25. So let's see what's the result we are getting. This would run for the various k values. 0.02 it is starting, and it will run up to 15. We have changed the values of k, so we will see that how the variation would be there for various coefficients. Okay, the code is running. So in the meanwhile, let's see here what it has shown. It has shown for the k equals to 0 means ceramic, and k1 up to infinite, that would be metal. Okay, so k is varied from ceramic to metal. Okay, so it is, if the k value is very large, then we can say it is a metal, and if k value is very small, means it's almost 0, we can say that okay, it is a ceramic, and in between the variation is done. So it is given for the in-plane displacements u and v. Okay, so we will also see our results for this, and it is shown for the transverse displacements. It's a ceramic, it is the least. Okay, and for the metal it is highest. We know that ceramic is brittle material, and it's not ductile, and it is very tough material, so it is having the least displacement, means very stiff material, whereas we know that metal is somehow uh, flexible, so therefore large displacements are occurring, and in between the ceramic and metal the variations are there with known coefficients. If k is equals to 1, then the displacement is here, and if the k, as the k is increasing, so we can see it's approaching towards the metal properties, so therefore the displacements are increasing. So yet, okay, now we will see that we got the results now. Let's see, it is the sigma yz, so that's the shear stress yz, and how it is varying we will see. K equals to 0.1 means it's almost, we can say it's a ceramic. Okay, and then that is the least stresses we can see, and then as k values are increasing, k 0.3, 0.5, 0.7, 1.0, 1.5 and all, so these are showing the characteristics of the metallic properties. Okay, similarly same for the sigma xz, then this is showing the sigma zz, then it is sigma yy. Okay, we can see that this dotted line is k equals to 0 means for the ceramic part, which is having the least stress. Okay, and other than that, as k is increasing, k equals to 0.3, then after this it is having the least part, second least, then k equals to 0.5, that's the yellow dashed line. Okay, then other this is the blue line, so it's increasing as we will see that k values are increasing, it's approaching like metallic characters, so large stress are increasing. Similarly, this is sigma xx, the same as it's also showing. Then from here we can see that this is a transverse displacement, so k equals to 0.1, this is the dotted line, so this is the least displacement, almost we can say that okay, it's 0.369 at the center or mid plane. Then for the red one, which is having k equals to 0.3, it is having 0.399, and it's increasing as the k values are increasing. So we say that as the k values are increasing means the properties are tending towards the metallic. So we can say that okay, k value is large, then it is metal. Okay, so this is having the largest displacement, that is 0.8517, while the ceramic part, that's having the least displacements, and it is 0.369. So if it is the material is completely made up of fully ceramic, then it would have the least displacements, while if it is made up of fully metals, it would have the largest displacements. But we know that both is having the drawback. If it is made up of fully ceramic, then we know that it's a tough material, means it is a brittle material, so therefore it would get cracked easily, while it's very good in thermal resistance, but it cannot resist the uh, vibrations and all, it will get cracked. While we know that the metallic part, metal is having that advantage that it is very ductile, it can take the vibrations and all, uh, but we know that for the high temperatures it gets buckles, so therefore the composition of both metallic and ceramic would be very helpful. Therefore in between these we use or we select as per our requirement, we design our functionally graded material plates. Okay, and then we can see that the in-plane displacements u2 and u1 and u2. Okay, so just we can see that okay, for the ceramic part, the least displacements, this is the dotted line. Okay, that's having the least displacements, and as k values are increasing, the displacements are also increasing, and the for k equals to 1.5, that's the maximum for the metallic part, it is having the maximum displacements at top and bottom. Okay, so thank you. We will close here, and in the next lecture, inshallah, we will move forward and we will see some more things about the functionally graded material plates. Thank you.